Hey! Hello everyone! I'm back with more mathematical logic. It's been a rough couple of weeks. But don't worry. Today we are good enough to go with our little mathematical logic intro course. Today we will go over a more elegant method for analyzing formulas and sets of formula for propositional logic. Truth tables are good as an introduction because they are very visually clear and completely exhaustive. They provide us with a full map of all possible combinations of the truth functions we can assign to a formula or sets of formula. Whether it's a formula or set of formula doesn't matter much because we can turn a set of formulas into a single formula by just adding conjunctions. When we want to study a set of formula, we basically want to study if the entire set of formula is true or false and under which conditions. So the logical connective that is true when everything is true, aka the conjunction, suits us just fine. We can just do that. So the distinction between a formula and set of formula is one we can gloss over. Anyways, so in previous sessions we went over truth tables and the idea of a truth function, an assignment of truth values for each and every propositional letter inside a set of formula, such that every letter has one and only one truth value, whether it is true or false, never both, and always one, at least one. So we call that a viable truth function for a set of formula. And if we find a truth assignment that makes the entire set of formula true, we call that truth function or truth assignment a model of the set of formula for whatever set we're talking about. Also, yeah, sets can be of one. A single element is still a set of one, so again, it's not it's difficult to understand because it requires putting language in a very technical mathematical way, but it's not a problem for our abstract formal setting to use those terms. Set of one is just fine. So if we want to find a model using truth tables, we do the whole mapping and then we just find one where in the main connective, the last truth connective that we use gives us true. And if that is true, then the entire formula or set of formula is true and we have a model under one particular assignment. If every truth function gives the formula true, then that formula is a tautology. If every truth assignment gives that formula false, then that formula is a contradiction, at least within the context of propositional logic. Now, all that's well and good, but the problem with truth tables is that they grow in complexity exponentially. for every new propositional letter, we are raising the exponent by 1. 2 propositional letters is 2 to the 2, so 4 rows, which is very easy to manage. 3 becomes 8, 2 to the 2 to the 2, 2 times 2 times 2, sorry, not to the 2. It's always 2 to the n, where n is the amount of unique propositional letters we have. So 1 is just 2, 2 is 4, 3 is 8, 4 is 16, 5 is 32, and that is about the number that becomes viable for humans to calculate. 64 is tedious. I've done 64, but I mean, whatever. 128 is torture. It's just, it gets very inefficient very fast. And yes, there's plenty of arguments or plenty of formula that use 6 or more propositional letters. Because the problem grows in complexity exponentially, that means that validating stuff, in the most general sense of stuff for propositional logic, using truth tables is computationally inefficient. It's a very brute force-like method. So yes, truth tables are good to get into, but there is, I mean, I want to say better. There's no such thing as plainly better, but the point is, truth tables have a hard limit. Not just because they grow exponentially, and that means that things get tedious really fast, but also because, as the text that we see on screen mentions, propositional logic is kind of like a propedeutic. It's not that useful because you cannot do or express a lot of mathematical relationships with propositional logic. The real stuff is first order logic. That is when you can actually do or start doing real mathematics. And the problem with first order logic in regards to truth tables is that first order logic has an infinite amount of possible truth assignments. Like, not just always one more, like a real infinite. And try as you might, you can never make a truth table with an infinite number of possible models. You just can't reach there. So we need a different method if we want to use certain type of analysis when we eventually study first order logic. So, because of the intrinsic computational inefficiency of truth tables, and because we just cannot use truth tables once we reach first order logic, most books, most courses recommend the development of, I heard them, okay, so actually this book calls them tableaux, which is French. There you go, propositional tableau. Which, if I recall correctly, also means table, as in truth tables, so let me check that. I don't wanna. It's not! A tableau is a vivid or graphic description. Oh. Or arrangement or layout. Interesting. Okay, never mind that. It's a false cognate. Anyways, so yeah, there's this method called tableaux, or tree proofs. We'll see why they're called tree proofs. And not only are they adequate for analyzing first-order logic, which is what we're really after, they also provide a lot of insights into computer programs, especially things or seeing computer programs as searches or plans. We'll see how soon. Anyways, this is not Mendelssohn. This is a beginner's guide to mathematical logic by Raymond Smullyan. Sorry to cherry pick from different books, but I like this explanation better for tree proofs or tableau. So let's read. Since we shall later be studying first-order logic, which is an enormous advance over propositional logic, and is, in fact, an adequate logic for virtually all of mathematics. That is true! That is fucked up and true. For 95% of human mathematics, you can just use first-order logic and a couple of new symbols, and you're good. The remaining 5% is the only interesting bits of mathematics, and, well, it's a big mess. But anyways, for first-order logic, the method of truth tables is far from sufficient. That is an understatement. And so we now turn to the method known as tableau, more precisely analytic tableau, which in this chapter will be treated at the elementary proposition level and which will later be extended onto first-order logic. Let us begin by noting that under any interpretation, the following 8 facts hold for any formulas x and y. In this book, this squiggly symbol is a negation. So if not a formula is true, then the formula is false. Intuitive. Negation is the switch. If not formula is false, then the formula itself is true. Remember the opposite. If the conjunction is true, then both are true. If the conjunction is false, then either one of them is false. Maybe both. But that case is superfluous, because if both x and y are false, then x is false, or x is false is also true. Either one of them was also going to be false if both are false. So it is redundant to add the third case that is superseded by this case. If x or y is true, then either is true or both are true. Same logic, but flipped. If we have the case in which both are true, it is superfluous. They are superseded by the fact that if both are true, then x is true and y is true. If x or y is false, then both have to be false. If x implication y or x implies y is true, then either x is false or y is true. Again, we have actually proven that the implication, which I prefer using p's and q's, is equivalent to not p or q. We have proven this in previous sessions. So we can just reduce the implication to the case of the third rule, which is the disjunction. If the implication is true, then either the first element is false or the second element is true. And we know it's false because negation of the element is true, and so on. Then that becomes the first rule. If the implication is false, then we know that this is false and this is false. So if the negation of p is false, then p is true. So the first element is true and the second is false. So if we wanted to, we can reduce all of our connectives to just negation, conjunction, and disjunction. In fact, we can reduce them to even one, but it becomes very non-manageable unless you're a computer. And we have a fifth symbol that we've been handling, which is the big conditional. But the big conditional is very simple. Let me use text. If x, I'll use the symbol. If x, if and only if y is true, then either x and y are true or x and y are false. If x, if and only if y is false, then either x is true and y is false, or x is false and y is true. Ah, big text. Yeah, but there we go. Basically, if the disjunction is true, if the disjunction, the big conditional is true, then we have two options. Either both are true or both are false. And if it's false, then we also have two options. Either one is true and the other is false, or vice versa. The first one is false and the other is true. We also saw previously that the big conditional can be broken down into two conditionals. X implies y and y implies x. So we're just doing this to have a broader, more encompassing rule system. And here Smulian mentions sign formula, which I guess is okay if you want to be rigorous, but we don't really need to. We have already used the more rigorous notion of truth functions. The interesting concept is just this term, the conjugate. The conjugate is just the switch. So negation is conjugate. It's another way of saying switch. It's just basically saying fx is a truth function that assigns to the formula x the value of false. Tx is a truth function that assigns the formula x the value of truth. Yeah, we don't really need this because we have a more rigorous defined notion, so we're just gonna skip this. Okay, so here's the actual good stuff. Before defining a tableau, we shall illustrate with an example. Suppose we wish to prove the formula P or Q and R implies P or Q and P or R. By proving here is we want to show that this formula is true under every model. We want to prove that it is a tautology. That is what it means to prove a formula in propositional logic. We do so with the following tableau, the explanation for which is given immediately following the tableau. Okay, so notice that if we want to prove something, it's odd that the tableau starts with assigning the formula false. We'll see why, but I'll explain, or rather, I'll give the answer and I'll prove the answer later. The answer is that tableau is a way of searching for viable models of a formula. So what we do here is reduction to absurdity. We're going to try and find a truth function that gives this formula false. If we cannot provide a single truth function which assigns this formula false, then that means that it is impossible to give it falsehood, which means it is necessarily true, which means it is always true under every truth function. So first we have, in step number 1, the formula we want to analyze, given the value of false. So we want to see if we can find a way of making this formula false. In order to make a conditional false, the first element, the antecedent, has to be true, and the second element, the consequent, has to be false. So I'm going to use a different color. I'm going to use cyan. So this is this, and this is this. The antecedent is giving the value of true, the consequent is giving the value of false. Now, we have a true disjunction and a false conjunction. Both have two possible situations in which they can be true. Or, well, the disjunction has two possible situations in which it can be true, and the conjunction has two possible situations in which it can be false. So we're going to split. We're going to branch off. That's why they're called tree proofs, because they start from like a root, and then they have branches. So we're going to analyze the formula in two. A disjunction is true when either the first element is true, which is this part, or the second element is true, which is this part. Now, we can only progress on this side by analyzing the only remaining unanalyzed formula, which is 3. But before we do that, let's analyze this conjunction, which is simple because the conjunction is true. It's only true when both elements are true. So if Q and R are true, then Q is true and R is true. Then we're going to analyze the third formula on both sides. And that formula once again splits off into two branches on each side. So in order for a conjunction to be false, either the first element is false or the second element is false. If the first element is false, then P or Q is false, which means that both have to be false. But, I'm going to use color red now, we assigned true to P here, and we assigned false to P here. That is a contradiction. That is not possible in our perfect, stagnant, logically frozen world. Hello, Rupert. Been revisiting through the bots and practicing in my head while I get a hang of LibreOffice. Salute. Hey! Good to know, Rupert. So because we have assigned P true on false, this branch, once the semester is over and fully locked in, good. I know you're gonna enter finals soon, so don't worry too much. Because we have assigned the same propositional letter to truth values, that is not possible, and thus this branch is closed. It closes with a contradiction. So this is not a viable model for the falsehood of the first formula. Let's go to the other side. So either P or Q has to be false, or P and R has to be false. P or R has to be false. But if P and R is false, then both sides to be false. So the same problem. P is given false and true at the same time. That's a contradiction. That is not possible. So let's go to this side. We analyze this formula, the falsehood of this conjunction. So either P or Q is false, and then we have similar problems. P, Q are false, but then we have Q being given the value of true here, and then giving the value of false here, which is contradiction, not viable. Thanks for the hydrate. And on the other part, we have R given the value of true and given the value of false at the same time, which is a contradiction, which is not viable. So this is just another way of saying what I just did. The idea is that we will recursively analyze formula. This formula can be recursively analyzed into constituent parts. And eventually, because our system, the amount of formulas that we have is finite, we will always reach we will always exhaust all possible branches if we follow certain rules precisely. In propositional logic, that is not going to be an issue. In first order logic, because we have a possibly infinite amount of objects, we may stumble into endless loops if we don't follow certain rules precisely. Anyways. As we construct this tableau, we are attempting to see if we can derive a contradiction from the assumption that the formula is false. Because if the negation of a formula is a contradiction, then the formula without the negation is a tautology. We proved this in the last session. Gamer Bakain says, Senpai, what do you mean you just didn't have power? Did FIFA do this? No, that was actually a storm. A storm approached and knocked some branches into the power lines, so we spent the last 16 hours without electricity. Fun times. Yeah, okay, that's very advanced Mexican. That is a correct expression. Good job. Anyways. And so our first line consists of this formula preceded by the letter F. So we are assuming that it is false to see if what happens then. Now a formula of the form X implies Y. Okay, that is what I just said. We just went through. We can skip this. Thus, in the language of tableau, both the truth of X and the falsehood of Y are direct consequences of the sign formula, the falsehood of the implication. The interesting bit is just this bit of lexicon. Direct consequence. We will be using the term direct consequence as a transformation of a formula done in a single step or rule. So we have indirect consequences, which we can arrive by more than one rule or the application of more than one rule, and direct consequences, which we can obtain by the single application of a single rule. And yeah, this is just what we just went through. We just in other words. The tableau is now completed in the sense that the consequence or consequences of any formula on any line have also been entered into the tableau properly. Every line of the tableau that can be used has now been used. A quick catch-up. The implied symbol is different from implies if and only because it isn't strictly conditional. No, they are different. It's just simple convenience. There is no like universal consensus on which symbols to use. Different schools and with different typewriters, because most of this shit was developed with typewriters, had like different like key sets. So sometimes the implication is they use the symbol, sometimes they use an arrow, sometimes they use a fancier arrow with 2 lines. For example, some people don't use this one because it can be confused visually with the less than sign or the greater than sign. So, for example, if you are dyslexic, many people who are dyslexic do not like to use the horseshoe symbol. This is also called the horseshoe symbol. But the people who were doing this with typewriters in the early 20th century, well, guess what? The horseshoe symbol is simply a U turned 45 degrees. And not everyone had like a fancy arrow symbol. So they make do with what they have. Now that is the implication symbol. The biconditional or equivalence symbol Sometimes it is used with 3 lines. But some people don't like using this one because it is visually similar to the identity symbol. And in mathematics, identity and equivalence are not the same. Identity is stronger than equivalence. Think literally. Equivalence, same value. Identity, identical, the same thing. Two things can have the same value without being the same thing. For example, you at your job. All of your fellow workers, you are equivalent to the whims of the bourgeoisie. But you're not identical as human beings. Identity is stronger than equivalence. So yeah, biconditional or equivalence is 3 horizontal lines, but some people also use like this, dual arrow lines, or dual arrow lines with double width, like this. So the biconditional is different from the implied symbol is different from if and only if because they do different things. The biconditional is for checking if 2 formulas have the same value. The conditional is to see if one formula implies the other, but not necessarily the other way around. A funny way, when I use examples like this or allegories, I am not being formal, okay? I am not defining the symbols in that way. I'm just saying this to provide more mental clarity. But they're just like joke examples. They are not strict definitions. Why can't I select you? There we go. Think of the biconditional as the super best buddies. Okay, Mr. Bytes, have a good one. Yeah, the biconditional is like the super best buddies. They always go to the same parties. If you ask them if they want ice cream, they will both say yes, like the Mario Brothers. It's like identical means both form and content are the same, while equivalent means that the 2 things are equivalent only in the content, for example. Not exactly. When I say that 2 times 2 is identical to 4, I can do something in mathematics very special, that is replacing. Let me be a little bit more abstract. If A is equal to B, and A is equal to C, I can replace any of the terms that are identical, because these are just multiple names for the same mathematical object. If A is equal to B and A is equal to C, what can I conclude from these 2 formulas? Maybe let's make it a little more concrete. Where's my text tool? I need to... Yes, but both of those are the premises. A equals B is the first premise, A equals C is the second premise. There is a new formula that we can derive or conclude from the following. Let me give it a little more flesh. Superman, yeah, you got it. Superman is Clark Kent. Superman is cal L. If Superman is Clark Kent and Superman is cal L, and yes, we can replace A with B, and thus brain friend. If A equals B and A equals C, if Superman is Clark Kent and Superman is Kal-El, then what is a new identity I can derive from this? B equals C. In this case, who is B and who is C? Tum tam tum tam tum tam tum tam tum tam tum tam tam da 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 da. Kal-El is Clark Kent. Exactly, yes. Here Superman is A, Clark Kent is B, Kal-El is C. So Clark Kent will be Kal-El. Who the fuck is Clark Kent be? I don't know. Some dude. But I cannot do this with equivalence. I cannot replace elements with equivalence. Equivalence only tells me that if something is true, and something, if and only if, is connected to something else, then the truth of one proves the proof of the other, the falsehood of one proves the falsehood of the other. But we're not talking about the same element. We're not saying they are the same thing. So the biconditional is more like the best buddies. You know that Alice is super very mega best friends with Bob. They are always together. So if you see one in a party, you know the other one is in the party as well. If you see one in the concert, you know the other one is in the concert as well. Alice and Bob are always together. So if you go to a party and you see Alice dancing, what do you know about Bob? If A, if and only if B. I'm gonna go to this side of the screen. If A, if and only if B, if Alice is always together with Bob, and you see Alice in the party, what do you know about Bob? Tum tam tum tam tum tam tum tam tum tam tum tam tam da 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 tum tam. Bob is gonna be with Alice. Yep. So this is a different type of relationship than this one. This is a material relationship. It means they are it means that one statement proves the other and vice versa. These two mathematical results, now that we are no longer in the realm of examples, this formula proves this formula, and this formula proves this formula, and they also depend on one another. They are not the same formula, but they are equivalent. They prove the same things. They always come together. While the conditional only goes in one direction. A implies B. The truth of A guarantees B, but B does not guarantee A. it doesn't go backwards. It's only in one direction. That is the main difference between the conditional and the biconditional or equivalence. Anyways, let's continue with the tableau. So once we have analyzed every single formula in the tableau, we say that the tableau is complete. There is no further recursion to be done. We have arrived to the propositional letters. Now, examining this tableau, let us look at the leftmost branch, which ends in line 13. We can see that the lines 4 and 12, two lines on this branch, are direct contradictions of each other. Finally, a proof of the Blow-Job brothers. Yes, the equivalence or the biconditional is a truth function of the Blow-Job brothers. They're always together. That's gonna be the clip of today. Okay, so yeah, we go back to this. 4 and 12, as we went through, assign the same value, the same letter P, true and false. That is a contradiction. That is not possible under our system, so they cannot both be true, and so we close the branch by putting a bar under 13, signifying that the branch leads to a contradiction, and so it's not a real possibility. Again, when we're talking about reality and possibility, we're talking about reality and possibility under our logic system, not about metaphysical reality. Trying to obtain metaphysics out of logical systems is a risky endeavor. I will not suggest it. Similarly, 14 and 4 contradict each other, and so on, so on, so on. We already did this. Thus, all branches lead to a contradiction, so the line 1 is untenable. Because we cannot make that formula false, that means the formula, the original formula, cannot be false under any interpretation, and so is a tautology. Which means it is proven, it is true under the system, it is true under every model. What we do in the tableau method is explore all possible scenarios in which a formula X could be false. Each branch of a completed tableau shows the situation in one of those possible scenarios. And the reason we could conclude that the original formula of our example could not ever be false is that we always reach its contradictions in following out every single possible scenario. Remarks. The numbers put to the left of the lines were only for the purpose of identification in the above explanations. We do not need them in the actual construction of the tableau. So yeah. That's just style or efficiency. We have thus better defined a complete tableau as one such that on all the open branches, all formulas of the branch that can be used have been used. We didn't see this situation happen, but if we find a single open branch and we have analyzed all relevant formula and the branch remains open, that means that we have a model for the falsehood of the original formula. And that is the end of the tableau. As soon as we find one single counterexample, we're done. We do not need to do any more. Now, these are the rules for the tableau. And we're going to skip them because we don't need those. Because instead of using true and false sign formula, we're going to use negations. Instead of saying, oh, what happens when X and Y, a conjunction is false? We're just going to say, well, I mean, when it is negated. This book uses the squiggly line, but again, different symbols for the negation include this, and also like a square, which I cannot do. Some systems use the square. I don't like the square. It is very easy to overlook. I prefer the squiggly line or this weird L. It is basically the same rules that we just saw before. When a disjunction is true, we make branches and we go one side is true, the other is true. When conjunction is true, either the first part is false and the second one is true, and so on and so on. And instead of finding contradictions by saying falsehood of P and truth of P, a contradiction is going to be when we find both P and not P, where P is any formula. As soon as we find any contradiction, any formula affirmed and negated at the same time in the same branch, that branch is closed, it's a contradiction. There is really no difference between this method and this one. This one is just more inefficient because we have to check the truth value or the sign formula of every formula. The only reason why it is included is because there are other logical systems, non-classical logics, in which truth, or rather falsehood and negation, do not map out so perfectly. There are systems in which not P is not the same as falsehood of P. But we're not gonna see those systems. I just like mentioning this because there is something this is a bit like getting into philosophy of logic, but the pitch is this. These methods are what we use to evaluate logic. And ideally, we want logic to evaluate human communication, debates, arguments, and speech, and so on. We may want the idea of correct reasoning. The problem is that correct reasoning under which system? There are a lot of logics or logical systems going around, and nobody has solved the question of which one is the correct logic. I personally do not believe there is a correct logic. I tried for 11 years of my life to find the answer of what is correct reasoning, and my answer at the moment is there may be something like correct reasoning, but formal abstract systems are not going to give us that solution. That is my personal philosophical posture. That is my stance. That does not mean you have to agree with me when you do this, but that is the explanation as to why I like saying this is true, or this is valid, or this works under this system, but there are others in which it doesn't work. So the reason why we have the system using sign formula is because not all systems function the same way as propositional logic, and we may need to use signed formula for other logical systems if we ever do non-classical logics. But because we're doing classical logic in this course, we don't have to worry about that. Not P is basically the same as saying P is false. P is true is basically the same as saying not P is false, and so on. Okay, so but this is the important bit. This is the important bit. We have toyed with the idea that if we have certain information, we can conclude or obtain new formulas or new presentations for that information already present. In formal settings, we call this logical consequence. And that is the main study of logic as a philosophical doctrine. Now, you can study logic in many different ways. You can study logic as a mathematician, as a computer scientist, even in electronics. No, that is not an invalid question, Rupert. That is, in fact, an insight I shared with my thesis. As far as I know, all programming languages are classic. They do not have, for example, contradictions. You cannot assign a Boolean in any programming language that I know simultaneously true and false. But the insight is that if you have multiple programming languages and they all function for different things and they all vibe and they all work together more or less well, not necessarily working together, but they work in parallel, and it's all fine, so can different logical systems exist simultaneously. But that is not a trivial argument, because the philosophical problem of all this is the philosophical problem of logical consequence. What does it mean for a conclusion to follow from a set of premises? Basically, how do we argue? Why should I believe in arguments? Why should I accept a new belief if it follows or doesn't follow from certain premises? The concept of it follows, that mental operation, is what is at play here. And it's not a small task, because we are playing for what is the rule of the game, the rule of giving and the rules of asking and giving reasons. Hello there, TSG Frank. How are you doing? Welcome in. So yeah, we're not going to deal with the philosophical problems of what does it mean for something to follow, what is logical consequence, but I want to mention that it is a problem. It is a big problem that we have been struggling with for, last I checked, at least 3,000 years ago, if you count the Hindu schools of logic. But for now, mathematically speaking, we will define logical consequence between a set of formula which we call the premises and a formula which we call the conclusion. And the idea of logical consequence, at least in propositional logic, is that every truth assignment that makes the premises true must also necessarily make the consequence true. What have you been missing up to now? I don't know when was the last time you checked in, but at least in this session we're going over the construction of tableaux or tree proofs. The example, the tree proof that we went over is this. Ignore the squiggles to the side. Is a method for recursively analyzing formula into its constituent most basic elements, the propositional letters, so that we can test if we can assign certain models to the formula. And a model is a truth function that assigns every propositional letter of a formula a value such that the entire formula is true. There's a way to see the VODs. Yes, all of the VODs are on my YouTube channel. All of the logic and basically all of the Saturday streams, which are about like more philosophical stuff, more technical stuff. They are there. The playlist for the logic stuff is that one. So you can check it during the week if you want to catch up. Okay, so yeah, these are 3 proofs we will go over. And the funny or useful thing about 3 proofs is that we can use them to test for logical consequence. We can also test for logical consequence using truth tables, but remember what I said starting the stream, that truth tables are computationally inefficient because they grow in complexity in an exponential fashion. So our more preferred method for complex formula, for formulas worth analyzing, is going to be tableaux. And for first order logic, which has an infinite amount of models, we cannot use truth tables at all, so we have to use tableaux. And we defined logical consequence for propositional logic such as a relation between 2 sets of formula. I'm going to use funny symbols. Certainly, more like commonly. Was that lambda? Oh man, it's been years since I've used the funny Greek letters. No, that is not lambda. What was that? Gamma. That is gamma. Die, but die. Yeah, we use alpha, beta, and gamma. Yeah, I remember now. It's all coming back. We use gamma for a set of formula. Usually, but not always, has more than one. And we will use the following symbol for logical consequence using semantic or truth functional methods. This is basically alpha. I guess the only difference between is like the serifs on the bottom, whatever. There, it kind of looks like an alpha now. So this means that every truth function that makes this true also has to make this true. It is, another way of saying it is impossible for this to be true and this to be false. If this happens, then this is not the case, and we drive a diagonal line through it, and we say it doesn't follow. So when philosophers and mathematicians, computer scientists, nerds basically say, well, that doesn't follow, or even more pedantically, that doesn't necessarily follow, we're not saying you're wrong. We're not saying it's false. We're not saying that your conclusion is factually untrue. We're just saying you did not provide enough backing for the conclusion with these premises, because there is at least one situation in which I can conceive of your premises being true and the consequence being false. That doesn't mean that the falsehood is materially the case. Things can be not a consequence without them being empirically false. Logical consequence is not a relationship between facts. It is a relationship between mathematical structures. Or not just facts as they are, but all possible ways of interpreting a fact. If you want to become like an early Wittgenstein fan, which I'm not too supportive about, but whatever. So notice where we're going with this. If you want to test for logical consequence, what we're going to do with Tableau is we're going to assign the premises true and the consequences false. Or, equally as valid, we're just going to put the premises P implies Q, Q implies R, and the negation of P implies R. In classical propositional logic, these two methods are the same. We could start with the entire chorizo of a formula, in which we just put the premise and all joined together by a conjunction, and then material implication P implies R. But we can get this from the first rule anyway, so we can obviate like the first step if we want to. I mean, we're not going to for the first times, but later on it'll become like second nature. So what we want to prove is that this is impossible. We cannot create a situation in which the premises are true and the consequence and the conclusions are not the conclusion of the consequence. The conclusion is false. So if we do the tableau for this and all the branches close, we have proven that this formula, P implies R, is a logical consequence of these premises. But as I said, we're not going to use sign formulas. We're just going to use negations instead. The only interesting new rule about this part is this: the double negation. If something is true, then its negation is false. But if the negation of something is false, then the negation of the thing, once again, is true. Basically, for every formula of propositional logic, it is equivalent to that formula negated twice. Because negations in propositional classical logic are switches, flicking the switch once, flicking the switch twice, puts you in the same spot as where you started. There's only two places. If you go to the other place once, then you switch. If you switch twice, you return where you were. We can prove this very easily with quick integer truth table. It's just one formula, even though in this case it's a meta variable, but whatever, it doesn't matter. We have proven that we can use meta variables like this, I think 2 sessions ago. So the formula is either true or false. If the negation of a truth is falsehood, the negation of a falsehood is truth, the negation of a falsehood is true, the negation of a truth is false. Wow, we ended up exactly where we started. And so truth is the same as true? Yes. Truth is equivalent to truth? Yes. Okay, we have now proven the double negation rule. So we can do this. If we find any double negations, we can just take them off. I wish there were a way to just mass select and delete all of my doodles. Okay, the rest of the rules are the same as what we just went through, but instead of falsehood, we put the negation symbol. Simple. Is this relevant? Just a generalization of negation. For any formula with a line above, we take a line above to be not the same formula but negated. If any formulas of the form P, where P is a propositional variable, which is finally the smallest element of our systems, propositional letters, then it's just the negation. If it is a complex formula, then we just one of the following. This is basically the things that are good, healthy mathematics, but not really interesting if we already understand what's going on. But this kind of shit is useful if you want to program something. Because computers do not understand what's going on. They need to be told explicitly how everything works. Okay, we say that we have proved that a formula X is a tautology, or simply said that we have proved the formula X if we have found a closed tableau starting with not X. Basically, if we put a formula, negate it, and all of the branches close, then we have proven the original formula without the negation. It's a tautology. And for arguments, we take all the premises and we add the conclusion as a negation. And instead of proving the formula, we prove the argument. And then we have exercises. Okay, we're going to do some exercises, but not in here. Tools, text selection. There we go. We're going to move to a more convenient drawing space. No. There we go. Professional streamer, everyone. So we're going to do this as a truth table. Easy. We want to see if the formula is proven, so the first thing we need to do is negate it. Because we have a negated implication that is only the case when the antecedent is true and the consequent is false. Because we also have a false or negated implication that is only the case when the antecedent is true and the consequent is false. Oh no! We have Q and not Q. Nani? Which means this branch immediately closes, which means that we have proven the formula Q always implies that P implies Q. What does it mean? Whenever a formula in propositional logic is true, then everything implies it. Which leads to some funny logical games, such as by saying, yesterday I had no electricity. So, it is logically true that if yesterday I had no electricity, which I will now... Oh, that's a very ugly... Why? Why am I using my pixel brush? I'm not drawing. Duh. With a Y. So, because yesterday I had no electricity, that means that the sports ball World Cup implies that yesterday I had no electricity. If there is a World Cup, football sports World Cup happening, then that implies that Samuel did not have electricity yesterday. This is logically true, because I didn't have electricity yesterday. What this tells us is that the implication is not factually relevant. It does not tell us anything about the world. There is no causal link or explanation between any of these two statements. It's just that because something is true, then everything implies it. Because the only way this can be false, remember, is if the antecedent is true and the consequent is false. But because this is true, this will never happen. So this will always be true in a very disappointing, not relevant way. But anyways, that was very easy. Let's go to the next exercise. Let's ignore the exercises from Smulian, and I have another set of exercises which are more fun and more helpful. Hope they don't involve sports ball. No, thankfully not. We're safe from the sports ball. It's just math and symbols. So this mess of symbols that didn't paste correctly is basically used to mean consequence. So the first three formula are the premises, and this P or S is the conclusion. So we're gonna negate the conclusion, and we're gonna test if this argument is valid or not. Valid meaning that every truth assignment that makes the premises true also makes the conclusion true. So we're gonna see if we can do this. By refutation. Okay, so I have implication, disjunction. The only formula that will not give me more branches is the last one. And generally speaking, I want to use rules that do not create branches first, because branches duplicate the amount of work I have to do. So the less branches I open and the more formulas that I analyze before branching, the more efficient my work becomes. So when is a disjunction false? Only when both elements are false. So from the last formula, I get that not P and not S. Also, I personally like to add like a check mark or a little symbol to know which formulas I have analyzed. So because I just analyzed the fourth formula, I want to put a check mark here. And this is not necessary. This is just for a memory tool. But it's not part of the formal system at all. It's just like a study aid. Now, I'm fucked. I have to open a branch. But another tip I can suggest is try to open branches that include elements that you have already gone over before. So R, Q, T, and so on. Yeah, it doesn't tell me anything. I just care about P or S. The only formula in which the same letter appears is the second one. So I want to analyze the second one. T implies P, so that is true. That means that either the first part is false or the second part is true. But here we have not P and P. That is a contradiction. I will close my branch right then and there. So I'm being efficient with my work. So I already analyzed the second formula. See, I immediately closed off this, so that will save me lots of work. Out of the remaining ones, might as well analyze the simpler one first, the one with less symbols, so R or Q. Let's go for the third formula. So this branches to either R, whoa, selection tool, what are you doing? There we go. Either R is true or Q is true. I don't have contradictions either way, but I have analyzed this formula. Now I have two branches and I have to open two branches on each side. So first formula, either the first part is false or the second one is true, and the same here. Either the first one is false or the second one is true. And I have analyzed this formula. Well, shit. I have an open branch. In this branch, no, it's not open because I have not T and T. Never mind. I almost missed it. See? That's a really cool part about tree proofs is that they are very visual. I think that's why they call them tableaux. Because you can just go backwards. You can do a backward search, start from the end and go whoop, 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 whoop. Oh no, T and not T, closed. Same here, T and not T, closed. Oops, missed a parenthesis here. Okay, so I have two branches open then, and I have to analyze them. A disjunction is false. That means that both elements are false. Not R and not Q. But here I have R and I have not R. Contradiction. And the same thing is going to happen here. I'm going to have not R and not Q. Contradiction. All of my branches have now closed, which means that the original argument without the negation is valid. This is a valid argument. So, chat, what do you think so far? One more exercise. Disjunctions are a really neat way of thinking. Well, I mean, it's just either this or the other or both. Just choices. Yeah, they are computationally the most efficient method, I think, that we have so far. Let me look for an invalid argument. I think this one is invalid, but hey, that's what we have this method. Let us check. So this will be the conclusion. So I'm going to put it all. And remember in the previous VODs between the three proofs and the method assigning a value to one term and deducing whether the argument is tautology or not, how much time is saved from the two tables. Yep. Yeah, and the most... So the thing is, truth tables actually beat trees when you have like 4 or maybe 5 letters. More than that, and tables tables lose. Computational complexity is not so much about which one wins in a specific case. It's more about how much the problem grows, or how it grows in terms of complexity, or how it grows in terms of time needed to compute the more elements it has. So trees grow by 2 by 2 by 2 by 2. For every truth function, no, not truth function, words. For every truth connective, the problem grows at worst by 2. And it is 2 plus 2 plus 2, maybe even times 2. So the worst case scenario, the tree grows by multiplication by 2. Best case scenario for a truth table, it grows exponentially. That means the exponent is growing. So yeah, trees grow in a much more manageable manner than truth tables. Okay, so I think this one should be invalid. So that means we should at least find one branch that is open. I have already negated the conclusion. This formula was the original conclusion. So let us analyze. All of these formula will create branches. So might as well look for the one that already has an element in my premises, which is either the first or third or fourth formula. Sorry, the second or fourth formula. The second one is still more complex, so I'm gonna go for the fourth one. If a conjunction is false, that means that either the first element is, okay, we're using squiggles in this one. Squiggle, squiggle. Either the first element is false, so not Q, and the second, squiggle, squiggle. Second element is false. Okay, I have double negation, which means that I can just take out the negations. Not Q is the same as Q, not P is the same as P. Okay, I cannot analyze 1, I have analyzed 4, so shit, I'm fucked. Nothing else I can do. Out of the remaining formula, 3 is simpler than 2, so fuck it, let's analyze 2. So if a disjunction is true, then either the first element is true or the second element is true. Either the first element is true or the second element is true. So far, nothing has crashed. Now I have to analyze the second formula. It's a implication, so either the first element is false or the second element is true. I used to have a program that ran on MS-DOS, I swear to God, MS-DOS, that was for doing truth trees more efficiently. Way more efficiently than drawing or doodling. I don't know if I can still get it or if I can run it on Linux on the year of our Lord 2026. But anyways, let's see if I have anything now. So this disjunction negated, so that means that both elements are false. So this is not R and not S. Not R is the same as R. So using another color, I have not R and R closed. Now let's go here. I have another implication, so again that splits. Either not P, the first element is false, or the second element is true, not Q. Okay, here I have Q and not Q. Contradiction. Not P is the same as P. Let's go backwards. P, S, Q, P. Oh shit! The branch is open. That means I have found one case in which the premises are true and the conclusion is false. Specifically, if P is true, S is true, and Q is true, that will make the premises true and the conclusion false. Let's double check. Just so we can all fully believe in the power of in the power of three proofs. So P has to be true. Okay, P is true. That checks. I'm going to use another color. I'm going to choose green. So P checks out. If Q is true, P is true, and S is true. If S is true, then that makes this disjunction true, because at least one element is true. If this is true, then this has to be true. So not P. Not P is false because P is true. Because this is false. Sorry, no, whoops. Because this is true, the negation is false. So if the antecedent is false, this is automatically true. True implies true. True. Checks out. Not R or S. S is true. If S is true, then this checks out. And then finally, the negation of not Q and not P. Both Q and P are true. So this is true. This is true. The negation is false. The negation is false. False on false, false. The negation of falsehood is true, which means that we fucked up because we don't want this to be true. We want this to be false. Duh. Okay, because we want this to be false, we want the conclusion to be false, then this has to be true. Oh yeah, no, no, wait. I fucked up. If we want we want this to be false. Okay, no, I'm being double stupid. Okay, I am lost my mental inventory. I am already measuring if this is false because I am measuring the negation. The original formula is without the negation. The negation I added in order to make the tree. Duh. So I want to make this false. I trip myself over with falsifying a negation. Sorry, computer brain. So yes, this is true. This is true. This is false. This is false. False and false. False. Which makes the negation true, which makes the original formula false. Yes, we have thus now proven that this argument is invalid. There is at least one situation in which the premises are true and the consequences are false. Ta-da! Now, let me go back to now, y'all can do this as homework if you want to. I want to see if there are, I mean, maybe I'll share better exercises. I mean, these ones are fine, just a little, okay, no, never mind. I'm being a bully. These are basic, they are fine, they're good for beginners. This is a good homework. Please screenshot the stream if you want to. If not, let me share this book. This is not Mendelssohn. This is Raymond Smullyan's A Beginner's Guide to Mathematical Logic. Just for the sake of reference, this is George Boole, this is Aristotle, and this is Kurt Gödel. This guy is one of the single most influential people in history, and you probably never heard of him. So yeah, if you want to get this book, it is A Beginner's Guide to Mathematical Logic by Raymond Smullyan. Unifying notation. Okay, this is just a way of reducing the system to just negation, conjunction, and disjunction, which is called, in Spanish, forma normal conjuntiva or forma normal disyuntiva, conjunctive normal form or disjunctive normal form. Basically, all you really need to do to have like the full set of Boolean logical gates is negation and conjunction, or negation and disjunction, or a single symbol that we have not defined, which is NAND or XOR, XNOR. No, not XOR, XNOR. Don't worry about those now. They are like really freak cases. They are mostly only useful if you want to test if something is Turing complete. If you want to, you can define this formula with implications as the same formula with conjunctions, which is not a pretty sight. Yeah. And here's the symbol for the single. There are two truth functions that can define the rest of the truth systems. And the only real use besides testing if something is Turing complete is launching rockets. If I recall correctly, one of the Apollo missions used an onboard rocket computer that was only programmed in NAND, which is the Sheffer stroke. Yeah. This, again, is not very useful in terms of content. This is useful in terms of practice for mental acuity. If you want to, just as a pure mental flex, you can define certain formulas only in terms of negation and conjunction or negation and disjunction, if you want to. That's like just pure brain homework. Another thing you can do to get a more intuitive idea of logical consequence is play Sudoku. Sudoku is a straightforward logical game in which once you understand the rules of the game, you can find that there is only one logical consequence in terms of there is only one possible number in this specific square. The mental process of eliminating all the possibilities except this one is very similar to our notion of logical consequence, in that there is no possibility in which this can all be true and not have the consequence. If we ever want to do metalogic, which will be like a distant third course to this, then this becomes a lot more relevant. But again, we're not going to do that. Today we're just going over 3 proofs. Let me check something really quick. Nope, I cannot find the program I used to use. I'll check if I can somehow find the program for both truth tables and... No, wait, no. It was not for truth tables. It was for deduction. Yeah, it was deduction and trees. So maybe it was the other one. Okay, never mind. This is gonna take a while. Not really necessary. I'm gonna do like. Wait, I did the first one. I'm gonna do the second one here, really quick. So. So I take the formula, and remember our first step is always negate the formula. Notice that this system uses square brackets. It's not necessary, just for visual clarity. They're welcome, but not necessary. So I put the entire formula in a new set of parentheses and negate it. Okay, so I have a implication negated. That means that the first part is true and the second part is false. So the first part is that, and the second part, false, is this. We're using squiggly lines today. Okay. Both formula do not cause branches, so I'll just analyze. The one that gives me more immediate material is the third formula. So, whoops, did I just change? All right, no, we're fine. We're fine. So the negation of implication, that means the first part is true and the second part is false. Oh no. My text box has become too small. Oh! What did I just do? What did I just do? Ah, panic, panic. See, this is why you don't trust. Oh, I see now. I can only do it. Oh, okay, all right. Yeah, better do this in this part of the screen. So we have analyzed this formula and this formula. So then I have another, which is a conjunction. So that means P implies Q and Q implies R. Both have to be true because a conjunction is true only when both parts are true. And the first one, okay, I'm gonna have to use pen on this, pen tool, because this one will branch. So I have, so I analyze this formula, so I have to analyze this one, which branches into either the first part, squiggly lines, is true, and the second one is false. The other way around. The first part is false, or the second one is true. So P and not P, we have a contradiction here, closes. And then I analyze Q implies R, which is either not Q, which will close because my Q is gonna look like 9s. This is not a dyslexia friendly stream. I'm so sorry. And then we have R, but then we have R and not R, contradiction, and that's a very mangled tree, but it works. Okay. Very important, our rules. I will copy and paste this on Blue Sky if you want to. Otherwise, just hell. In fact, I can do it right now. I'm going to put this on my Blue Sky. Homework. Yeah, no need to make you all suffer. There we go. Yay! I will now share that post on Blue Sky if you want to. I really don't know what else to say. Any questions, any doubts about how to use trees? Remember that trees are a method for refutation. We always want to start with negating the formula. We want to see, basically we're testing if it breaks. We're trying to find, if a branch is open, remember, we find a counterexample. Okay, I'll just close this PDF because fuck deleting all that on the line. Okay, then that is all I have for y'all today. Check my Blue Sky for the homework. And I'll see you next week when we're gonna close off our semantic methods, or basically the methods that deal with assigning values to formula. Oh yeah, well, I have some very bad news about that, but today is not the stream to do it. Today we just focus on the logic. I'll see ya. I don't think I'm gonna keep streaming on Tuesdays because my students on Tuesdays they're drawing a bit longer. Maybe I'll see you on Monday with Cryptmaster. I want to return to Cryptmaster, but I think it'll have to be on Mondays. Anyways, I'll check how we do it during how I'll do it during Sunday. Anyways, this was Samuel, your friendly internet uncle that wants to help you get into philosophy, helping you get into mathematical logic. I wish you the best of luck with your 3 proofs, and I'll see you later. Bye-bye!